Um, okay, so let's do that, or let's plan on doing number 64. Anybody have one that they want to look at on Appendix E before number 64? 62. Yeah, we'll do that one right before we do 64. Okay. How about one in the 40s? 42. Okay, that would be a good one. All right, so all right, there we go. So number 42. Now, when you logged in, did everybody get logged in and did it transfer some files? Okay, it should. Okay, it should transfer a couple of files. Now, whenever that thing comes up, yeah. 5.5, isn't it? No, you have to go on from the home screen. You go 5 for settings, and then 5 for login. So it's 5.5, and then you're logged. Okay, so that should be. But what you should do is, yeah, put the hat on, log in, everything. And in this case, I sent you. So, all right. So 42. 42 says. Remind me what it says. LN. No. Log base 6 of radical 6. Okay, there are two ways that you could work this. Okay, one way would be to rewrite. This is probably the shorter of the two ways. Rewrite radical 6 as 6 to the 1/2 power. Remember that? Okay. So, all right, and so now what can we do with that? There's some kind of cancel. Yeah, basically, I mean, if you really understand logs, it's just 1/2. I mean, because the base 6 inside and the base 6 of the log, it's like square and square root. They cancel each other out. All right, but here's the property that's real handy for us this year that I want to make sure everybody understands. What can I do with this 1/2? Pull it out front, okay? This comes in so handy, and we use this a lot, that I want to make sure everybody gets that. And now log of 6 base 6 is just 1. So 1/2 times 1, and that's just 1/2. Okay? So that's one way to do it. Another way to do it is to take this and just let it equal x, right? Just call it, let it equal x. And now we can convert it to exponential form. So we can take this base 6 raised to this power x, and that's got to equal square root of 6. And then we say, okay, 6 to the x is equal to 6 to the 1/2. And for those two to be equal, x has to equal 1/2. So that's equal to 1/2. So either of those is okay. I really like the one on the left better just because it's more useful in things that we do as we go through the year. Okay? What else? What's 44 say? Okay? So what you want to do is a very similar thing to what we just did on that one. Since this is a base 3, I would really love to make 27 as a base 3. What is 27 as a base 3? 3 to the third, but since it's on the bottom, it'd be 3 to the negative 3. And then we can do exactly the same thing. We bring the negative 3 down in front. So the theme in all of those, in the 40s there, is to just try to match up those bases. Okay, and log 3 base 3 is just 1, and so this just comes out to be negative 3. Okay? All right. And so as I was coming around, I did notice on a number of people's papers where you just had one answer. I mean, you didn't have a word written down, you didn't do anything. Now, maybe you're really good with logs and you just could see 3 to the negative 3 in your head and do all that. Or maybe you just typed in your calculator, I don't know. But hopefully it was the first one, all right? Because most of the time when we have to do these is in a no calculator scenario, okay? All right, what else? How about one like 50, one in the 50s here? 58, yeah, I do want to look at 58, and I tell you what, let's look at 50 and 52 just real quick, because I think there's something to be learned from those as well. 50, now what you're told here is that log base 4 of A is 2.1, correct? So on 50, it says log base 4 of 1 over A. Well, that's A to the negative 1, right? 1 over A is A to the negative 1, and now as we've learned here, what can we do? Bring the negative 1 out in front, and so we get this, and of course we know that that is 2.1, so negative 1 times 2.1 would be negative 2.1, correct? All right, so that's wasn't too bad, but then we get to 52, and it says log base 2 of A. Now that's a problem because this is base 4. Any ideas? Well, yeah, you think, well, it's half, so would that be half of that? It's twice as much. Now, yes, it turns out it is. Now, it seems kind of like magic math to do that, we just do that, but it turns out to be true. Now, let me show you why. Because if I call this x, then I'm going to do that exponential thing. So this would be 2 to the x equals a. And if I do that same thing up here, 4 to the 2.1 equals a, right? Everybody with me on what I did there? Okay, well if this equals a and this equals a, then those two have to both be the same. So 2 to the x has to equal 4 to the 2.1. Now I can't really compare those because they're different bases. How can I get them to be the same base? Let's turn 4 into 2 squared. So we have that. And what do you do when you have a power and a power? You multiply it. So this becomes 2 to the x equals 2 to the 4.2. Okay, so x has got to equal 4.2. So this thing up here has got to be 4.2. Okay? So that's how we could look at that one. All right. Now I want to talk about 58. 58 says that f of x equals 20 e to, is it 0.1? 0.1x. And then they tell you that f of x is equal to 80. Right? So this is similar to what 56 was about. Basically what we're going to do is we're going to substitute 80 in here for f of x. So we're going to get 80 equals 20 e to the 0.1x. So what do I do from there? Divide by 20, gives me 4, then what? I can either change base, or the one I like is do natural log of both sides. Now, again, it doesn't matter to me. But I do want you to know this one where we do the log of both sides, because there are some times I think this comes in a little handy. The change of base, the problem with change of base is if this, like if we have 4 equals 2 to the x, the only reason I don't like change of base is because then you've got a log base 2 of 4 equals x, and then you got this log base 2 thing, and then you got to change it to natural log from there. So I just like to give the natural logs right away. But again, it'll work out the same either way, so it doesn't really matter. All right, so over here we have ln4. Now we've got this power which we can bring down in front, right? So 0.1x times ln e. Over here we got ln4. What's ln e? 1. 0.1x times 1 is 0.1x. So 0.1x equals ln4. Divide by 0.1, what's that? That's the same as dividing by 1/10 is the same as timing by 10. So 10 ln4. Now, if you cheated, that might be too strong a word. I'm perfectly fine with this answer. But if you cheated and typed this into your calculator, it did not give you 10 ln4, did it? No one's going to admit that they cheated and typed it in their calculator. Or maybe no one did. You cheated. And what did it give you? Oh, you got it to a decimal. You remember what it said before the decimal, or did you even do it without a decimal? Well, let's just do it right now. Let's go to the calculator and let's go into the scratch pad onto the calculator part. And I'm just going to type in 10. Where's LN? I'm a long ways away here. That's the e to the x. I could just type it in, right? 10 ln 4, right? Now watch what happens when you type in 10 ln 4 and you hit enter. Now why did it do that? Why is that simplified? What did it do? 4 is the same as 2 squared, right? And 2 squared in here, you can bring the 2 down in front, right? And it's 20 ln 2. Okay? Now, why is that important? Because I will accept 10 ln 4. If you had as an answer, this was a no calculator quiz we were doing, and you worked through that problem, I would accept 10 ln 4. I do not expect you to simplify that down. It doesn't matter. The AP test, it doesn't matter. However, on the AP test, this will not show up usually in the free response section. You know, in the free, as you remember when you read the course description guide, right? Hopefully you remember. Remember that one of the questions was, what's the AP test made up of, right? It's 4 parts. One part is no calculator multiple choice. There are 55 questions. No, there are 28 questions. There are 28 questions. You get 55 minutes. Okay? Second part is calculator multiple choice. There are 17 questions. You get 50 minutes. Okay, now let's see. 28 questions, 55 minutes. That's about 2 minutes a question on the no calculator. On the calculator part, it's 17 questions, 50 minutes. So it's about 3 minutes per question, right? You get more time on the calculator part. They figure it takes a while to punch the buttons and stuff, so maybe you're not as fast. The free response section has 4 questions. You get an hour for 4 questions where you don't get to use your calculator. And those 4 questions have multiple parts, A, B, C, D. And then you get a half hour for 2 questions where you do get to use your calculator. So 6 free response questions make up half the test, and 50, 28, 17, 45, right? 45 questions make up the multiple choice part, the other half of your grade. So 6 free response questions, 45 multiple choice questions, each counts a half, okay? They are not, on those 6 free response questions, going to ask you trig and algebra stuff. They want to focus on the calculus stuff. But where they will test you on this prerequisite stuff, trig, angles, and natural log, and exponential stuff, is on the no calculator multiple choice, the one where you have 28 questions. And here's what they'll do. You'll have a question that will come out, and you'll work it out. It's no calculator. You'll work it out, and you'll get 10 ln 4. And you'll look at your 5 choices. And 10 ln 4 won't be one. But 20 ln 2 will be one. See what I'm saying? So you have to know about those simplifying rules and things like that when it comes to a situation like that. Okay? And also on your calculator, if you work it out and you say, hey, I'm going to check my answer on my calculator, and you had 10 ln 4 and they had 20 ln 2, you got to know that you're still right. Okay? That the calculator is not, you don't want to sit there and think you screwed up when in reality you were right. So it is important to understand those things. All right, let's go on to number 64. No, wait, we were going to look at 62 real quick, right? What did 62 say? It said f of 1. Was it f of 1? G of 1? H of 1? H of 1 equals 10. Didn't somebody want to see 62? Okay, all right. H of 1 equals 10, and what did they tell us? H of x equals what? To the kx. All right. So h of 1 equals 10 means what? We're going to plug 1 in for x, and then that's going to equal 10. So we'll have 20e. We put a 1 in for x, so that's 20e to the k. Okay, so isn't this just like the one we just did? We'll divide by 20, and what's that? 1/2? 0.5 e to the k, and then we'll do the ln on both sides. Or this is a pretty easy one, you just turn in the ln form, right? ln of e to the k. Now what can I do over here? Bring the k down front. ln e is just 1, so k equals ln 1/2. Is that all they wanted? They just say find k. So there's it, right? ln 1/2. Yes. Oh, did we finish it? Yeah, 10 ln 4. Right? Because we were supposed to find x. Yeah. 10 ln 4. Right here when we divide by 0.1. Yeah, actually, I would have accepted this. Right here at the end, I divide both sides by 0.1. So I get ln 4 over 0.1. But 0.1 is 1/10. So if you divide by 1/10, it's the same as 10 to the 2. So I kind of do that, yeah. Actually, technically, I would probably, on some situations, I would just accept that too. Okay. See, simplifying is a funny thing. Simplifying, my kind of basic rule of simplifying, and I'll try to tell you at the various things we're doing, but usually, if you need it, if it's helpful to simplify it for something that you have to go on to farther down the problem, then you should simplify. If it's your final answer, I'm not sure it's that big a deal. Okay? All right. So in 62, we just kind of go through that, right? And we just plug that in and we solve. All right, 64. Now in 64, they told you j of x equals a e to the kx. Now what's different here is there's two unknowns. You don't know k or you don't know a. So it's kind of been a progression here. As we've worked through the problems, they've kind of told us some parts and not others, and we have to solve for them. Here they don't tell us hardly anything. Right? I mean, there isn't even a number in the problem anyway. Yet. I mean, it's all letters, right? But then they tell us j of 1 is 5, and they tell us j of 3 is 10. Let me tell you what kind of problem this is going to be when we get to the calculus part. There's something called Newton's law of cooling. And Newton's law of cooling is an exponential equation. And exponential means it goes up really fast like this, or it comes down and levels off like this. That's an exponential equation. Okay, and we're going to be reviewing those things. But Newton's law of cooling says that if I had a hot cup of coffee sitting here on the table, that it would cool faster in the beginning, right? Does that make sense? If this coffee was like 180 degrees maybe, and it was sitting here, it would cool pretty fast. But as it gets down towards room temperature, right, it's going to kind of start leveling off. And it's not going to cool as fast, okay? And so that's going to be an exponential equation. It's called Newton's law of cooling. Now, one way we can predict, so because we know it's going to follow an exponential pattern, if we just take two pieces of information, because there's two unknowns that are going to determine how fast it cools. One of the unknowns is going to be A, and that's going to be determined by our initial temperature, okay? And K is going to be determined. The value of K is going to be determined by variables within the situation. For example, if it's in a styrofoam cup, it won't cool as fast as if it was in like a ceramic mug, right? In a styrofoam cup, it'll insulate it more, and so it won't cool as fast. And so K would represent those kind of quantities, all right? So what this would represent is we take two temperature readings. At 1 minute, we take a temperature reading, and at 3 minutes, we take a temperature reading. And based on those two factors, we can figure out what A and K are, and then we can predict the rest of the time what the temperature will be, okay, at any given time. So that would be an example problem where we have to do something like this. All right, so what we're going to do is we're first going to put 1 in for x and make that equal 5. So we get 5 equals a e to the 1k, correct? Put 1 in for x and I got that. Now there's not really much else I can do with that, so I'm going to come over here because I got an a and a k and the 2 things, so there's not much I can do, okay? So I'm going to come over here to this other stuff they gave me. I'm going to put a 3 in for x and set that equal to 10. So get a, e, and put a 3 in for x, that would be 3k. Now what I have here is two equations to unknown, which stuff you did in algebra 1, did in algebra 2. Two equations to unknown. What do we do with that? Substitute. Meaning let's solve for one of them. Well, the easy one would be to go over here and solve for a. So let's go over here and let's divide by e to the k. So we're going to have 5 over e to the k, right? Does that sound reasonable? Okay, we're going to do that. Okay, and so what So that was the first part of substitution, is to solve for one of the variables, A, and then do what? Put it in the other equation. We're going to stick that over there for that A right there. So we're going to have 10 equals, and in place of that A, we're going to have 5 over e to the k, and then we're going to have e to the 3k. Okay? So now tell me what I can do with that. So I have 5e to the 2k, right? Because I'll subtract those powers, right? 3k take away 1k is 2k, so, because we're dividing there. All right, and now, doesn't this look familiar? Isn't this just like 58? Right, same thing. We divide by 5 now at this point, we get 2, e to the 2k, we're going to have to log both sides. What am I going to get over here when I do the natural log of both sides? 2k. Divide by 2. Now, you're going to find that I don't like dividing very much. I'd rather use fractions, and you're going to find out the same thing as we go through the year. So I'd rather not write that ln2 divided by 2. I'd rather write that 1/2 ln2. Some things that we do as we go through the year, it's just going to be much better to think of that as a 1/2 or a 0.5 instead of a divide by 2. Now, we're not quite done because they want us to find k and a, so what do we do with that? Put it back into this one. So we get a equals 5 over e to the 1/2 ln2. And for right now, that's good enough. That's good enough. Now, hopefully you can see, and if you looked up this up in the back or you typed it in your calculator or something, I mean, hopefully you're sitting there and it kind of makes you uncomfortable to leave it like that, okay? That'd be a good feeling. If you're uncomfortable leaving it like that, that's a good thing. Because what could you do with this? You could move the 1/2 up in front, right? Or, I mean, up into there. You have 2 to the 1/2, which is what? Root 2? Square root 2. And then you have e to the ln square root 2. Well, what's e to the ln? They cancel each other out. It's like square and square root again. So e to the ln square root 2 is just square root 2. So this whole bottom is just square root 2. So it's 5 over square root 2. And then that probably bothers you too, leaving a square root on the bottom. So you could do that, okay? But I don't really care about that at this point. So you can just leave it like that. Okay? What I care about is kind of the mechanics of these solving these exponentials, because we will run into that. And we want to, and when we get to it, we don't want to have to go through it over and over. You know, I mean, we will. I mean, you'll get to practice a few, but I mean, that's what's going to happen. Okay? All right. Appendix G. Problem number 4. Okay, one of the things that one of the classic calculus problems, and we will study this in chapter 4, is called optimization. Optimization. Finding the optimum outcome. And it's usually a maximum or a minimum. And we're going to do 2 examples here. In this case, we want to find the maximum profit. We want to make some mugs, and we want to find out how much should we charge to get a maximum profit. Now, it says in the problem that it costs us 60 cents to make a mug. And it says we can sell them for $1. Right? Now that's 40 cents profit, correct? And if we sell them for $1, we'll sell how many? 1,000 of them, right? If we sell them for $1, we'll make 1,000 of them. But if we drop the price, what happens? Sell more. Well, I don't know about make more, but we'll sell more, right? But we'll sell more. But does that mean you'll make more? Well, remember, we're selling them for less, right? So we're making more of them, but we're selling them for less. So they're kind of working against each other. So the idea is, at what point should we set the price to make the most profit, right? Because if the price is too high, you don't sell enough. Price is too low, you sell more, but you're not making as much, right? So at what point should we set this price to make the right, to make the most profit we can? Okay, so that's the dilemma we have. So now, what they try to do in number 4 with part A, B, C, and D is they try to lead you into the problem. It's kind of like what they tried to do on 1 also. They try to give you some hints as to what to do. Okay, I'm going to kind of skip that part because we usually don't operate our story problems that way. So I'm just going to start writing down some stuff. Now, I am going to take one suggestion they had, which was let X be the number of price reductions right? We could have let X be the number of mugs. We could have let X be the price we're looking for. But it turns out a pretty good way to do it is let X be how many price reductions we have. So the first thing I'm going to do is I'm just going to focus on one mug. And how much can I make on one mug? Well, I can make $1, right? Because I can sell it for $1. But then I got to subtract off the 60 cents that it cost me to make the mug. And I got to subtract off the amount of my price reduction. So how much would I subtract for my price reduction? Because every price reduction is going to take a penny off of what I make on that mug. Every price reduction is going to take off a penny. So I got $1 that I'm going to have for selling the mug, minus the 60 cents it cost me, minus any price reductions that I have. Okay, so I'll simplify that real quick. So that's 40 cents minus 0.01x. So that's one mug. That's my profit on one mug. Right? Everybody okay with that? So if I don't have any price reductions, I'm going to make 40 cents. If I don't have any price reductions, I'm going to make 40 cents. If I have one price reduction, I'll make 39 cents. If I have two price reductions, I'll make 38 cents, right? Okay, so that's going to be my profit on one mug. All right, so then how many mugs am I going to sell? What's it say? I'm going to make 1,000 if I don't have any price reductions. But if I reduce the price, what happens? I could get more. So I could add more mugs. How many mugs? 50 for every price reduction. And X is so that's why it was smart to choose X to be the price reductions, because everything was based off the price reductions. My profit on a mug is dependent on the price reductions, and how many I sell is dependent on the price reductions. So we let X be the price reduction. So that's going to be how many I sell right there. Well, okay, if this is my profit on one mug, then I'll just multiply that by how many mugs I'm going to sell. Correct? Okay, so forgetting what it says there in parts A, B, C, and all that, we've done A, we've done B. Find a function that's a total profit. That's it right there. That's my total profit. Let's call it P. P of X equals, there's my total profit, so that's part C. And then they say, and then they want to know what's the best price. They say hint. Let's do a graph of that. Okay, so let's do it. So let's go to our scratch pad. Let's go to our graph screen. Let's hit tab to open up that F1 of X window. Okay, now wait a minute. Why am I doing all this? Time out. Oops. Oh wait, I'm going to take off the okay, eeny, meeny, miny. The presenter is Zach. Okay? All right, Zach. Now everybody else go ahead and do this too. All right? So we're going to let's put in that equation that we just had. So left parenthesis, what was it, 0.40 minus 0.01x, and then, then left parenthesis, and then what was it, 1,000 plus 50x. Now, any predictions as to what this graph's going to look like? Think FOIL, right? We're going to FOIL that out. There's going to be an x squared term. It's a quadratic. It's going to be a negative x squared term. So we should have an upside down parabola, right? Oh, so where's our max profit going to be? Up at the top, right? That's our profit. So there is going to be a max. Okay? It's going to be up at the top. Okay. So now we're not seeing the graph. We'll go ahead and hit enter. And we're not seeing the graph because our window's no good, right? So now we got to think about domain and range. And that's why those problems always ask you about domain in Appendix G. So let's go to our window, under our menu, our window settings. Okay, under menu, you have window settings. And what's our x in this problem? price reductions. So we might have 0. That'd be our minimum price reduction. How many price reductions are we going to have? We're talking about a penny. It costs us 60 cents to make, so we better not have more than 40, right? If we had 40 price reductions, we'd really be in trouble. We'd be losing money. So we better not have more than 40. So we can set that as our max. Our Y is what? Profit. So we better not have negative profit, so that better be 0. What's our most profit? Remember, we started out saying 1,000. We could sell 1,000, and we're going to make 40 cents on every one. So what's 40 cents times 1,000? 400. So 400, but it might be more than that. So maybe let's go 600, maybe. I don't know, put 600 as a profit. Okay? So you got to think through. What does X stand for? What does Y stand for? What do I got? Okay, there it is. That looks pretty nice. That's a upside down parabola. Now we want to trace. And this does something kind of neat with tracing. Now we're not going to get away with this very often because we're going to have to show our calculus work. See, right now we've done no calculus in this problem. Okay, this is all just algebra. All right. At this point, we would do some calculus to find the maximum. We're going to cheat here a little bit. We're just going to trace on the graph. So hit your left arrow there, Zach, and trace. And it's going to do something cool when you get to the maximum. It's going to tell you, but you got to go kind of slow once you get there. So as soon as you get up there close, slow down a little bit. Slow down. Okay, there you go. Boop, boop, boop. Look at that. It says maximum right there. Okay. So there's the point, 10,450. So what's that mean? What's the 10 mean? 10 is X. That's the number of price reductions. So what's that mean? What's that mean? 10 pennies off the price. And so our best price? 90 cents. Our best price would be 90 cents because they said $1, right? $1 is what the price we're going to set, but we did 10 price reductions, 10 pennies. So 90 cents is our best price. That'll give us the max profit. Okay? There you go. All right. Thank you, Zach. When you get to that point?
Yeah.
No, I got used to it. No, well, here's the thing. We're not going to be able to count on that anyway. I mean, it's not something we use. It's kind of a nice thing to do, but I don't know. That's weird. I don't know. Now yours didn't say maximum. Maybe it's just the first time you did it. Huh. I have no idea. Move your cursor around there. Move the cursor around.
Mine just did. I went down.
You went the down arrow?
Yeah,
Hit the down
arrow.
Hit down arrow. Hit down arrow. Hit on that point again and hit the down arrow.
Oh, if you just hit the down arrow, it will just go straight to the max. Oh, yeah.
When you hit the down arrow, it just
Yeah.
went straight to maximum?
Once. It didn't do it this time. But
Oh.
last time.
Yeah. Huh. Well, here's what the down arrow normally does, I think. If you had like 3 graphs all on the screen, F1, F2, F3, the down and up arrows would take you back and forth between them. I think is normally what it would do. So I'm not sure why it does maximum. Since we only have one on the screen, maybe we hit down arrow, it just takes you to it all over again or something. I don't know. That's weird. Okay. Anyway, let's move on. Number 11. We got one more to do here, and then we got get into something else. Now, number 11. This is one of my favorite all-time problems. We got the snowmobiler or whatever. What is the snowmobiler? Yeah. He's stranded, probably injured. Oh no, is he out of gas?
Yeah.
Oh yeah. Okay, we don't want to turn the news. Okay, so he's out of gas. Okay, so he's down here, probably freezing cold, 20 below, blizzard. There's a service station right here. Right? Isn't this what it would look like? They said it was east of his position. So I think that now the 6, I believe, would be here. Is that what you had? Okay, I think that's right. Now, he's got a dilemma. He obviously can walk faster on the road than he can in the snow. So if he goes straight up to the road and then along the road, that's going to be longer, but he'll spend more time on the road where he can walk faster. Or he can trudge through the snow all the way in a straight line. Now that's shorter, but it's slower. So, and then of course the other thing he could do is go part way. He could kind of go part way, cut to the road, and then get on the road. So this is a minimum problem. What is the minimum amount of time? Right? Mere seconds may make the difference whether he lives or dies. Okay? That's what I love about this problem. So what he's going to do is he's going to get his calculator out, his calculator book, and he's going to sit there and he's going to figure out exactly where to go so he gets there in the minimum amount of time. All right. So, but anyway, it's a minimum problem, so we do it. But so I'm just going to say this. Let's just say he picked some point in between. And they told you to let R equal what? What was R supposed to be? Yeah. Wouldn't that be that right there? Okay. Now, if he decides to not walk on the road at all, if he decides to go straight through, then what's R? 0. Right? That's the least he could walk on the road, as if he doesn't, if none at all. He could not walk on the road. And what's the most he could walk on the road? 6. If he decides to go straight up, I guess he could go west and then come back, but that'd be stupid. So if he goes straight up and then walk 6, so R could be anywhere between 0 and 6. Okay, so we could take into account those two situations or anything in between if we draw a picture like this. All right, so if that is R, then what's this piece right here? 6 minus R. Okay, so then this piece, the hypotenuse, would be the distance he travels in the snow. Well, that's just going to be the Pythagorean theorem. So the square root of 3 squared plus this side squared. We could FOIL that, but there's no reason to yet. Okay? So that's going to be the distance that he's in the snow. Now, we know we got distance equals velocity or rate times time. I don't want to use R again, so let's use speed. We'll do speed. Distance equals speed times time. So since we know their distances, R and then this, we don't know them, but I mean we have an expression for them. So we've got an expression for distance. We need to divide by speed. So we need to take distance divided by speed. So in the snow, his distance is this. Because this is what they wanted you to do. They wanted you to get an equation for time. Okay, so that's his distance, and what's his speed? 3. Now, we'll add that to how much time it takes him on the road. Now, the time on the road would be his distance on the road, which is R, over 4. There you go. That should be an equation in terms of R. It's going to be a function T of R, right? Time with respect to R. And that's all they wanted you to do, was to write an expression for time in terms of R. Okay? But it was just a distance equals rate times time problem, but you had to draw a picture, you had to set it up, pick a variable, which they had told you what to do. Now, here's what would happen. We're not going to take the time to do this, but if we would go graph this, but it is a graph that kind of comes. I'm recording this, so my computer's bogging down. It's not a parabola, but it is going to be kind of a graph that's going to come down and then go back up. In other words, what's going to happen is if R is little, like if he doesn't walk on the road at all, right, he's going to be fairly slow. It's going to take more time because he's traveling slower. But the more he walks on the road, the less time it takes him. But at some point back here somewhere, all of a sudden, now it starts taking him more time again because now he's going longer. And the length of his trip is overtaking the faster speed. And so somewhere in here, there's an optimum place to go to get there in the minimum time. And so, again, that's a big part of calculus, and that's something we'll be doing in chapter 4. Okay? All right. Good job. Now, what we want to do is get your exploration stuff out now. And we're going to kind of wrap this up, tie all this together, tie the last 3-4 days together here with these big ideas as far as rate of change. And yesterday we did area, this definite interval thing with area. under the curve, okay? We counted squares, and we did all that. It's called the definite integral. All right, now, so you're going to go through exploration 4, and it's going to talk to you about find the area geometrically. That just means count squares, do the area. When you get to number 5, I'll probably start talking to you and helping you as you get into number 4. I'm going to draw something up there on the board that'll help you. I'll draw it on my picture there. But and then when you get to number 5, you're going to use one of those things that I sent to you. It's called Exploration 4. Okay. So on number 5, it says put this program in your grapher. Well, I've sent that to you. Okay? All right, so I'm going to give you 10, 15 minutes or whatever to work here, get started on this, and then we'll kind of come back together and discuss. You just get that? You just read that? Yeah, you're right. This is his other daughter. That Leia's younger sister that no one knows about. Yeah, pay attention to the units, right? That's important. Stop.